Go ahead and get started. Welcome to Visual Spectrum Analysis with WiSpy and Chanalyzer. My name is Trent Cutler, and I've been training people how to use spectrum analysis tools, packet analysis tools, and site survey tools for about 5 years. And you can find some of my online training videos at YouTube, so it would be youtube.com/metageektrent, and I've got spectrum analysis videos, I've got packet analysis videos, site survey videos, and general Wi-Fi videos, all at that particular YouTube channel. So go ahead to that website and subscribe to the YouTube channel. Now we also have at metageek.net, we are the creators of the Insider free Wi-Fi scanner, and we have used that technology to make all of our other tools better. So we started out making a USB spectrum analyzer. It was the smallest spectrum analyzer in the world, and we found out that a lot of people were using our spectrum analyzer to troubleshoot Wi-Fi networks. So we decided to take data from a computer and data from a USB spectrum analyzer, combine them so we can show which Wi-Fi networks are currently being affected by interference. So that became very popular. So whatever you have in the free Wi-Fi scanner Insider, that's going to be also available in our spectrum analysis tool. And if you aren't incredibly familiar with spectrum analysis, that's okay. We're going to get into all the basic fundamentals. This is going to be kind of an intro Wi-Fi troubleshooting webinar, so you should be able to catch up and fully understand what a spectrum analyzer does by the end of this presentation. We also have other presentations. For example, we do a packet analysis presentation. Those are on Wednesdays at the same time as this one, and then on Thursdays, every other Thursday, we do a design considerations for dual band Wi-Fi. And in that presentation, we'll talk about what you need to know before you implement a 5 gigahertz capable Wi-Fi network and a 2.4 gigahertz capable network. At metageek.net, we actually resell site survey applications. So these are kind of the super enhanced versions of Insider, where you can take a map or a floor plan and input it into the you can put it into the site survey application, and ask around a map. You can actually see where the dead zones are and what areas are lacking coverage. So if you have questions about any of those tools, feel free to ask me after the presentation. I'd be happy to answer any of your questions. We also have a great support team. Joel Crane is actually on the webinar, so I'm going to make him a presenter. So if you have questions, he can actually help ask them. So anytime you have questions, go ahead and ask them. Okay, so let's talk about the two basic Wi-Fi bands that we have, the 2.4 gigahertz and the 5 gigahertz. And you'll notice immediately we have this kind of insider-looking graph. And I know most of you, this is your first webinar you've ever attended. I'm gonna spend a little bit more time on the basics, but we have something that kind of looks like Insider here, and we see the boxy shapes that Insider typically draws, and in the background we have these extra colors. And this is what a spectrum analyzer can show us. It shows us all the noise and how congested it is. And if you see something that is red and yellow, that indicates that that channel is more saturated or more congested than what Insider is showing you. So we can see which channel has the most noise on it. And we can see which channel has the least noise. So if you look right around channel 1, we see that channel 1 has a lot more blues. Okay. Now up above it, this is where we have the Wi-Fi channels as they would appear in a spectrum analyzer. And most of you have used a Wi-Fi scanner called Insider, and you are one step ahead of a lot of people. You already know how to look at Wi-Fi in terms of the spectrum overlap. And in the 2.4 gigahertz, we have 3 non-overlapping channels. That means you should only use channels 1, 6, and 11. If you take anything out of this presentation, let it be this. You should only use channels 1, 6, and 11 in the 2.4 gigahertz. For example, if I were to choose Wi-Fi channel 3 and a lot of access points will default to Wi-Fi channel 3, but it will create a Wi-Fi network that overlaps with Wi-Fi channel 1 and Wi-Fi channel 6. Now that means you are going to cause interference for any Wi-Fi networks on channels 1 and channel 6, and those networks are also going to cause interference for you. Now in Wi-Fi, and this is going to be quite a surprise to some of you, but in Wi-Fi it is better to share a channel than it is to overlap one. Okay, so it's better to be able to listen to another person talk fully, wait for them to finish, and then talk on your own, rather than kind of talk at the same time, being able to cooperate. So we really expect people to share channels 1, 6, and 11 from here on out after this presentation. The 2.4 gigahertz, this is where a lot of people first deployed Wi-Fi because it had greater range. That meant they could put one access point in and it would cover a lot of range. And that was okay because the speeds weren't that good, and there wasn't a lot of Wi-Fi. But now if you turn on Insider or another free Wi-Fi scan, you'll notice that there's a lot of Wi-Fi going on, and that's because we have congestion or saturation in the 2.4 gigahertz. There's just so much Wi-Fi going on. And wireless is half duplex. That means only one device gets to talk at a time. So the more networks you see on the same channel, the more time you have to wait. So you have to wait for everyone to finish talking before you can start talking. So a lot of Wi-Fi networks on your channel is going to cause a lot of congestion. Now the 2.4 gigahertz, we have 3 non-overlapping channels, 1, 6, and 11. That means there's only 3. So if there is interference, you only have 3 channels to choose from. The 5 gigahertz is a different story. This is where we're going to see greater performance. We're going to see the newer technology, so 802.11n is in the 5 gigahertz, and we also have 802.11ac. 802.11ac can go up to 6.9 gigabits per second over Wi-Fi. Okay, we're not there yet, but we are seeing very, very fast speeds in the 5 gigahertz using 802.11ac. We can expect greater performance in the 5 gigahertz for 2 reasons. The 5 gigahertz indoors does not go as far as the 2.4 gigahertz. So we're not going to hear as much. And we also have more channels to choose from. Now if you look at the colors in the 2.4 gigahertz, we see a lot of reds and we see a lot of greens and yellows. And if we look at the colors with the spectrum analyzer, we see some blues but a lot of black. So that means that this frequency range is largely unused. It's untouched. That means if you were to put a Wi-Fi network in the 5 gigahertz, you would be able to accomplish the fastest speeds possible because no one else is using it. Whereas if you were to use a 2.4 gigahertz, let's say you put a network on channel 11, you are not going to get very good speeds. That's because there's other networks on that particular channel. Now some people don't like the 5 gigahertz because it has lower indoor range. Well, think of it like this. The more devices you hear, the less time you have to talk. So sometimes it's greater to not hear as many other people because then you're going to have better time to talk. So apartments, that's where the 5 gigahertz is going to be the best option because you have 24 non-overlapping channels. That means if someone is on another channel, you have plenty of others to choose, and you also have lower indoor range. Okay, so spectrum analysis, it's really quite a simple thing. We are looking at just RF waves, and we care about the frequency, and we are going to visualize it in a little bit different way. So if you look at this blue line, the height of it represents how loud or how powerful it is. This is the measurement of amplitude, and some of you will call this signal strength or dBm. And it looks like my drawing tools is not working, so I won't draw anymore. But the blue spike is how we are going to visualize that particular wave with a spectrum analyzer. And we can see that the two waves, the orange and the blue, are separate from each other. They're separate frequencies, and the orange one is not as powerful as the blue one. Now what we are interested in is seeing when something overlaps or talks at the same time as this orange line and creates a taller spike, meaning it's louder. So think about it like this. If we were sitting in a conference room and all of us were talking and someone walked in with an air horn, now that air horn is going to be louder than all of us, so as soon as that air horn goes off, we can't hear each other. So the taller or louder something is indicates well, it just indicates the loudness of it. And so we're going to look for things on the same frequency as Wi-Fi. For example, if this is channel 2, this is channel 1. We are interested in seeing if there is something very loud, or maybe if there's something like this. We'll get into that a little bit more. But just think of it like that. We are just measuring the amplitude levels of anything that is transmitting in the 2.4 gigahertz. It doesn't matter if it's Wi-Fi. It doesn't matter if it's a cordless phone. We are just looking at the raw amplitude levels of everything. Now, why does this matter? Well, it matters because wireless is half duplex. That means only one device can transmit at a time. So all of your Wi-Fi devices, all of your Zigbee devices, they're all sitting there waiting for their turn to talk. So the iPad transmits, and the recipient says, got it. I received that frame. And when he receives it, he sends an acknowledgement saying, hey, I received your frame, and then they say, cool, we're done. And once that acknowledgement, that orange color, once that is sent, that means it is someone else's turn to talk. Now what happens if there's interference? Well, interference is going to create something like this. And the recipient is going to say, I don't know what that was. It was garbled. It was garbage. It didn't make any sense to me. So he does not send his acknowledgement this time. He does not send it. And so the original transmitter, he does not receive an acknowledgement, so he sends it again, and this is called the retransmission. Okay, so now instead of using up a certain amount of airtime just once, he has to use up that airtime twice. And when he has to repeat himself, everyone else has to wait longer. And then finally, the recipient says, okay, I got your retransmission, and then he sends the acknowledgement, and that conversation is done, and now it is someone else's turn to talk. How that looks in kind of a aerial view, we have an access point that transmits data for an iPad, and that iPad receives the frame, so it goes like this, but it also goes omnidirectional. So everyone else gets to hear that transmission, and they say, okay, well, I guess he's talking, so I'm going to power off and I'm going to wait. Now the problem happens when there's something else that's transmitting at the same time. Let's say this is a cordless phone, and it causes a collision here. Well, everyone else is stuck waiting for that interference to finish or for some other device to stop talking. And sometimes these devices won't stop talking. And so everyone sits there waiting, and they can't hear anything because there's the equivalent of an air horn in the environment just constantly going off. And these are things that you need to use a spectrum analyzer to view. But let's talk about the three types of interference first. There are two types of interference that are Wi-Fi created, and then there's one other type that is non-Wi-Fi. So the first type is co-channel interference, and I always use the pie example. Think of a channel like a pie. You can share a pie with 100 people, but everyone gets a very, very small slice of pie. That's the equivalent of sharing a channel with a bunch of other Wi-Fi devices. Everyone has to wait for their turn to talk, so the more devices that there are to talk, the less time you get. So this is what happens when you have one access point and you bring in, let's say, 100 iPads. Everyone is very, very slow. The same thing is true when you're in an environment with a lot of other Wi-Fi networks. It doesn't have to be your own Wi-Fi network. It could be your neighbor who is on the same channel. Let's say your neighbor has a whole bunch of devices. Well, guess what? You are sharing that channel. You have to wait for them to finish talking. We call this co-channel interference. So every station and access point on the same channel competes for the time to talk. Now the other type of interference in the 2.4 gigahertz is adjacent channel interference, and this is when we have a Wi-Fi network on channel 1, and then we also have a Wi-Fi network on channel 3, and then we also have a Wi-Fi network on channel 6, and we have a Wi-Fi network on channel 9. Okay, they overlap. That means that they can't cooperate because this is as much as they hear of each other. They only hear a small section. Think of it like this: if I were to speak and you only heard 25% of what I said, how would you know I was done talking? Okay, so it's very difficult to cooperate when you're on overlapping channels. When you're on the same channel, you can cooperate. When you're on different channels, you can't. So what ends up happening is they start transmitting at the same time and corrupting 50, 75% of the conversation of each other, and then they have to send it again, and as they send it again, they're going to transmit at the same time, and they're going to keep causing problems in for both of the Wi-Fi networks. So it's better to share channels than it is to overlap them. In my design considerations for dual band Wi-Fi presentation, we'll talk about how you can plan and design a Wi-Fi network in the 2.4 gigahertz by separating out and reusing 2.4 gigahertz channels. So if you have the opportunity, register for that webinar. I'd be happy to show you what you need to do for the 2.4 gigahertz when you design wireless networks. Now, non-Wi-Fi interference, this is the last type of interference in the 2.4 gigahertz. This is the most severe. This is the one that you have been blind to if you haven't used a spectrum analyzer. I know that some of you do have a spectrum analyzer and you're just looking how to use it a little bit better, but this is the one that you bought it for. This is the one that you walk into an area and you get no throughput. You know that you have signal strength, but there is nothing there. Well, a spectrum analyzer is going to give you that kind of visibility into what is transmitting on that particular channel. It's going to say, hey, there's a cordless phone here. Hey, there's Bluetooth here. There's a wireless mouse here. There's a wireless subwoofer here. Now, someone asked about the next webinar on the design for dual band considerations. I believe you'll have to check our website, metageek.net/webinars. They're usually every other Thursday, so you'll have to register. I believe there isn't one this Thursday, but there is one next Thursday. I should know my own schedule a little bit better. So these are the tools that metageek creates that help you identify types of interference or troubleshoot different types of interference. So Insider, it's a great tool for looking at Wi-Fi networks that are overlapping. So you can see a Wi-Fi network on channel 1 and a Wi-Fi network on channel 2, and you say, oh, whoa, no, stop. Let's change that. This technology was also built into Chanalyzer. So Chanalyzer, you can troubleshoot adjacent channel interference and non-Wi-Fi interference. Now, if you look on channel 6, we have something that does not look like Wi-Fi. It doesn't create that box shape. It creates this spike of activity. This spike of activity, it does not look like a Wi-Fi thing, so this means that it's non-Wi-Fi. Another thing that we can notice is that it's taller. When it is taller, that means it is louder. So when something is louder, that means it is going to be more problematic. It's louder than your Wi-Fi network, so most likely you're going to hear more of the interference than you are of your own network. The last type is co-channel interference. This is something that you can only really troubleshoot if you have a special packet analysis tool. So packet analysis allows you to listen to all of the Wi-Fi devices. So you can hear the traffic created by iPads. You can hear the traffic created by smartphones. You can hear the traffic created by a Kindle or a laptop. You can hear it all, and you can say, oh my gosh, they are taking up so much of the actual channel that I have no idea. Maybe I should implement another access point or something else to relieve that congestion. Okay, so spectrum analysis allows us to avoid interference. And interference is something when we have another transmitter on the same channel. So let's say we have something that, like that spike that we saw earlier, it's not the shape of Wi-Fi. Wi-Fi is going to be that boxy shape, or it's going to be a curved shape. It's definitely not that shape. It's the spike. And we notice that it's taller. So it's on the same channel. This is channel 6. And we see it there, and we say, okay, well, that's probably the problem that we have been encountering. Now, if I change my Wi-Fi network to channel 1, and we still see that transmitter on channel 6, that means I have avoided the interference. They're using different frequencies. We're cool. No big deal. Okay, so you can avoid interference. Sometimes in the 2.4 gigahertz, since you only have 3 channels to use, you can't avoid it. You need to get rid of whatever is transmitting. And the only way you can get rid of that transmitter is by finding it, by tracking it down. And the only way you can track it down is by having a device that can show you the activity. A Wi-Fi card can't show you that. You are going to have you're going to need special hardware. And what that special hardware does is it tracks all the noise similar to similar to a microphone. Okay, when you start playing some music on your computer and it has that little visual application, it has that bouncing line, and when there's loud noises or the bass steps in, the line bounces up and down. Well, that's all a spectrum analyzer does. It shows you the raw activity, of anything that it's transmitting, okay? And we take that and we say, okay, you have a Wi-Fi network here and it's on channel 5. That's not a standard channel, and this is going against my rules, but I just needed to create this visual image so you can understand what I'm saying. So we have a Wi-Fi network on channel 5, and then we have a non-Wi-Fi transmitter that is A, taller, that means it's louder, and then the color represents how constant the noise is. Now red represents constant noise, so when you see red, that means stop. This is bad. This is something that is loud and constant like an air horn. Now we can have tall and blue. If you notice right here we have tall and blue, but that blue color represents non-constant noise. So it's not very constant, it's more like a clap. It's infrequent. Okay, so we can have a conversation and someone claps or they closes a book and it's very infrequent. It does not interrupt the conversation. But when we see something that's tall and red, we say, whoa, what is that? That is not good. That's problematic. I need to find that. Now someone asked, what is an automatic method to avoid or prevent interference? I really wish there was an automatic method to avoid or prevent interference. Now, some devices like your access points will have kind of an auto selection. Okay, unfortunately, that auto selection is done by a Wi-Fi card. A Wi-Fi card does not have a spectrum analyzer built into it, so all it hears is other Wi-Fi networks. It could listen to a channel and it says, "I don't hear any Wi-Fi," so that means it's good. But the problem is it doesn't hear any Wi-Fi because there's something else transmitting that is so loud that it drowns out all of the other Wi-Fi networks. So sometimes those automatic channel selection tools can be very, very bad. They always choose the worst channel, and the worst channel is the one that has interference. So right now there isn't an automatic one. Some of the vendors have implemented spectrum analysis into their access points. I know that Cisco has a very good solution that's called the Clean Air solution that will automatically avoid interference. Okay, so let's talk about the symptoms of interference. And most of you have probably encountered something like this. We have the regular traffic in green, so we see kind of a flat line of regular traffic, and then all of a sudden it drops out completely. So everything is going along just fine. The access point logs show that it did not go down. Everything was functioning correctly. However, the traffic dropped off completely. So that includes the regular traffic and the retransmissions. Okay. In the second example, we see that the speed's cut in half. For whatever reason that is, the speed's cut in half, and there's no logs to indicate that something went wrong with the hardware. In the last example, we see the regular traffic drop, and then we also see the retransmissions increase. Okay, so we see just about the same amount of Wi-Fi activity, but the overall message is getting duplicated. So instead of moving on to the next part of the conversation, he's repeating himself more often. So let's look at what a spectrum analyzer can show us. Now here we see the flat top shape that we've been talking about that Wi-Fi makes. So when you use Insider, Insider represents what a Wi-Fi network is going to look like to a spectrum analyzer. Okay, Insider is just going to show you the signal strength of an access point. Doesn't show you how talkative it is or how much activity that is. That is up to a spectrum analyzer to do. So we see that this shape is again tall, which means it's loud, and then we also see that it's red, which means it's constant. So there's constant traffic going through, as we can see here, and here, and here. Constant traffic, okay? Now, if we were to look at these snapshots to see what happened with a spectrum analyzer, what it's going to look like is going to be on the right-hand side. Now, look here. We have a spike of red activity that is tall and red. Now tall and red indicates noise like an air horn, for example. So it's tall, meaning it's loud, and it's red, meaning it's constant. And it's also on the same channel. Now when that thing came on, it caused everything to drop out completely. So now the flat top shape that we were seeing earlier earlier is no longer red, it's going green, and it's kind of fading out. And that's because something else came on and was transmitting louder and taller. So that meant that the access point said, whoa, someone else is talking, I'm going to back off and I'm going to wait for them to finish talking. Well, unfortunately, they will wait indefinitely when there's something else transmitting on that particular channel. Now the next example might surprise some of you. That's because we see something like this. It kind of creates a mountain shape and it spills over. If you look here, it spills over into the Wi-Fi network on channel 11. Okay, and it's not constant. It's definitely green, so it means that it's probably 40% utilization. So it's not transmitting all of the time, but it is transmitting, and it's releasing RF activity. Now this is a microwave oven. So if any of you have a microwave oven to cook food, or you've been in an office environment where they had several microwave ovens, these things are going to leak RF energy into the 2.4 gigahertz. And you have no idea how much each microwave oven is going to leak unless you check it with a spectrum analyzer. So if you walk up to a microwave oven with a laptop and you have the spectrum analyzer running, start an upload or start a download, and then turn on the microwave oven. You'll notice this exact same pattern. You'll see the microwave oven spilling over into the Wi-Fi and causing some throughput. Now this happens in office environments. They'll cook their lunch, and then they'll sit down at their desk and they'll start browsing things on their smartphone, and things aren't working, and that's because other people are cooking their food on the microwave oven. Now, the last example, this is a little bit more difficult to see. Keep in mind that in the symptoms, we see that the regular traffic went down, and then it started duplicating its traffic. So it was repeating itself. So we didn't see a loss in total output from the Wi-Fi. It was just less efficient. So again, it's just as constant as it was, that flat top shape, but we saw something that was causing it to repeat itself more often. And if you look in the background, we do see these blue spikes. Now these blue spikes, if I were to take a blue comb, and flip it upwards so the teeth were facing upwards, you would see blue teeth. And this represents Bluetooth. Bluetooth headsets, Bluetooth wireless keyboards, Bluetooth mice. These are never ever going to bring down a wireless network, but they are going to cause the retransmissions and cause inefficiencies in the wireless network. Now, a Bluetooth device has 79 channels. It transmits on all of them about 1,600 times a second. So it goes from one to another to another to another and transmits on all of them. This is a technique used by some devices to avoid interference. So if there is something on, let's say, channel 11 like we see here, it will encounter some interference, but it still has room on other channels to transmit on. So it expects to encounter interference like a Wi-Fi network. Okay, so before we get into the live demonstration, I just want to talk about what a spectrum analyzer is doing. It's very similar to that yellow bouncing line that helps you visualize what music looks like. So if you look here, we have this yellow bouncing line. In the center, we see that it's loud, and on the sides, we see that it's quiet. So we know that something is transmitting right around, let's say, Wi-Fi channels 149 and 153. Now, our tool visualizes it in terms of how constant this yellow bouncing line is. So when you see that it's green here, we see that it is somewhat constant. Now let's talk about patterns of transmitters. Now every single device that transmits in the 2.4 or 5 gigahertz is going to follow some sort of rule or some sort of protocol. And over time, this is going to come out as a pattern. And this is what they call modulation. So every single device, how it creates zeros and ones is going to be modulation. And 802.11b or legacy devices, this is anything that transmits at 1 to 5.5 or 11 megabits per second. you will notice that it will create a curved shape like we see here. And to a spectrum analyzer, we'll see it like this. So this represents a curved shape of activity. As we go up, so even if you have an 802.11n network, you'll still see curved patterns. That's because they are transmitting all of their frames at lower data rates. As we go up, we're going to see flat top shapes, so faster data rates. So if you were to do a download or start an upload, you will see a flat top shape. And this is the modulation type of 802.11g and 802.11n. Now 802.11a also makes that flat top shape. However, 802.11a is only in the 5 gigahertz band. So you'll notice that flat top shape here. With its little shoulders, and you'll see it all over. Okay. Now, in the 5 gigahertz, we can use a spectrum analyzer to know what is the best channel and what is the worst channel. If you look here, channel 56 has something that is tall, which means it's loud, and it has something that is tall and constant, or tall and red, which means it's loud and constant. So that would be the worst channel to choose. And if we look around Wi-Fi channel 132, we see that it is virtually unused. It's mostly black. So putting a Wi-Fi network on channel 132, hey, you just picked a channel and you did it with a tool that is better than Insider. Instead of counting Wi-Fi networks, you based on congestion. So we can say right around channel 56, someone is doing a lot of downloads. This is a bad channel. And then right around 132, I don't see any activity. There's no talking. That's a good channel. Now 802.11n is also going to make that flat top shape. However, part of 802.11 allows for 802.11 is for 40 megahertz wide channel. So instead of taking up just 20 megahertz wide, 802.11n can take up 40 megahertz. So we combine flat top shapes and we can have one larger transmission. This is how we get 150, 300, 450 megabits per second as we start using the adjacent channel and we start talking a lot more. So let's get into a live demonstration of a spectrum analyzer. And in this demonstration, we are actually going to look at 3 things. We're going to look at the density graph, we're going to look at the waterfall view, and the channels table. So these are the basic pieces of spectrum analysis. Everything from there is kind of an extra feature. We'll touch on them lightly. You can ask questions about them. I don't mind answering them, but I want to make sure everyone understands these reasonably well. So if you do have the tool, you can actually go out and start using it today. And give me 1 second to get this started. Okay, you should be able to see my screen now. And the first thing you'll notice up here in the top, we have a yellow bouncing line, and this is exactly what my time environment looks like. So it's kind of like listening or watching that visualization thing on your screen when you listen to music, but in this case, we're looking at my real-time activity. Okay, and if you look at the bottom, the x-axis is my frequency labels. In the software, I can change this to Wi-Fi channels. So up in the main menu, I can change this to Wi-Fi channels. Now you'll see channels 1 through 11. And you'll also see channels 12, 13, 14, depending on where you live. These are able channels to use. Now on the left-hand side, we have a time span. This allows, we can change this. Nothing really changes in the top view, but if you notice, this green box goes longer and shorter. Okay, this is our time span. This is how we create fun and interesting calculations. For example, in the rolling 1 minute or in the past 1 minute, we can track what the average and we can track what the maximum values are. So here's the average and the max and the current. Okay, so that's just in the past 1 minute. So if something loud was to come on, we would see it in the max. If something that was loud and constant, we would see it in the average. Now, those are very useful, mostly spectrum analysis geeks really like those calculations, but I'm going to show you the most useful visualization. This one is called color by utilization. So up in the top, this is going to be the percentage thing. If you select this, this is going to be that kind of color depth that we are talking about. So if something is loud and constant, we will see it here. Right now we see a lot of blue, and I'm going to press pause so we can talk about this real quick. Now we see blue, and it's tall, okay? But because it's blue, it means that it's not as constant, okay? And we see something that's blue here, and it's shorter, which means it's not as loud. So when it's not as loud, that means it's further away from us. And then we see something that's a little bit taller here, still not very loud, okay? If we were to make a judge on which channel to use, it would be kind of a wash between channel 11 and channel 1, okay? And the reason for that is because channel 6 has some red activity. We see some constant noise on that particular channel. Okay, so let's talk about the waterfall view. And I'm going to turn off the color by utilization real quick. So I want you to look at the yellow bouncing line that we see up here at the top. Okay, this yellow bouncing line, we convert this yellow bouncing line into colors in the pane below. Now, it looks like the matrix, but I want you to notice a few things about this. This is kind of like a seismometer or something that you would use to measure earthquakes. So when an earthquake happens, it goes from a little scribble to a big scribble. Well, when something is loud, we're going to use colors to visualize that. Now pay attention to the top pane. If you notice, we have a very tall yellow bouncing line that is constant. You know exactly when I turned that on. It was about 10:38 and 40 seconds. Okay. And instead of using a big scribble, we are going to use colors. So when something is loud, it's red. And you know exactly when I turned it off because you will see it in the waterfall. It goes back to its typical display of bouncing lines. So those red dots represent high or loud instances, and the green dots represent medium, you know, kind of a not quite as loud amplitude reading. Now if I turn that transmitter on, you'll see it come back on in the waterfall view, and it'll start going downward. Now, and if I change the channel, you'll see that it changed channels. Okay, there's no break between the two. It just went to a different frequency. Okay, you can use this waterfall view to find things. So it's an amplitude history. So if I were to walk away from an air horn, that air horn is going to get quieter as I get further away. The same thing is true as if I were to walk away from this transmitter, we're going to notice the color changes. So it's not as red anymore, and I can walk away further. And as I walk closer to it, we'll notice that it gets more red until it's saturated again. Okay, so this is visual representation of how loud something was. Okay, now if I turn on the color by utilization again, what do you notice about this? We see something that is tall and we see something that is red. Okay, I'm going to press pause so I can draw on this again. Here we see something that is tall, red, that represents an air horn. We should see that reflected in the channels table. Okay, now the channels table at the bottom of the screen is going to be kind of your channel picking. Okay, so if you're going to pick a channel, you're going to use this. This is going to give you the best possible choice because this is going to grade channels based on the amount of saturation. So how many devices are transmitting? What kind of noise? What is the level of noise on that particular channel? Well, channel 6 has the lowest grade possible. It has a grade of 4.7. The highest you can, so you can see here, the highest grade you can get is 100. Anything below 60 is a failing grade. So we'll notice channel 1 has an 87. That's pretty good. And channel 11 has a grade of 90.9. If you were to open up a spectrum analyzer, you would say, okay, I see something here on channel 6, but I also notice channel 11 is good and channel 1 is pretty much good. So if I place my Wi-Fi networks on channels 1 and 11, I can avoid that interference. Okay. Sometimes avoiding the interference isn't an option. You need to get rid of it because it's causing noise on every single channel. So let's talk about how you can find this. Now I'm using Chanalyzer Pro. Chanalyzer Pro does a lot of fun things. Okay. On the left hand side you'll see this navigation tool. I can go back in time, I can press pause, I can press play, and I can evaluate different instances in time. Okay, that's very useful because right now I'm still recording all of the data, but if I need to evaluate the channel over time, look and see how when I select a different time range, we'll see that channel 1 has a different grade. So right now the grade is 71.4. If I go to a different point in time, we see that it's 91.5. All I need to do is look at this amplitude history kind of browser. We call it the waterfall navigation. I can see that there's some instances where channel 1 looked a little bit busier. And when it was busy, the grade went down. The more devices were talking, that means there's less time for other devices to talk. It's also easy for me to find the instances of interference. I know immediately when something was transmitting, and I can jump to it very, very quickly. And I can say, oh, wow, look at that. That is bad. I can also say, well, you know, I'm walking onto the second floor, and I can create some notes for myself. Okay, I can go between the two while I'm still recording in a certain area. Okay. Now, one important thing about spectrum analysis, what good is a spectrum analyzer if it doesn't help you find a transmitter? And that's what I want to show you right now. This is a feature in the Chanalyzer Pro software, and this is going to help you find anything a little bit better. So you can click and drag across whatever is transmitting, like we see here, and you can click Finder. Now this is going to create a bouncing green line, a line that goes up and down, and this is going to be very similar to kind of like a metal detector. So as you get closer to things, it's going to get taller. As you get further away, it's going to get lower. Okay. So as I walk away from a transmitter, we'll notice that it drops down. And as I get closer to it, we'll see that it starts getting louder and louder. Okay? So it doesn't matter what is transmitting. As long as you can see it with the spectrum analyzer, you can find it. Now, if you have a directional antenna, attach it to the spectrum analyzer, and instead of kind of walking around playing bumper cars, the directional antenna will help you know the direction that you should walk to find it. Okay? And once you find it, you'll notice that it immediately stops broadcasting on that particular channel. So it drops off. And I always say you haven't found it until you have unplugged it. And you can see immediately when I unplugged it that everything dropped off completely. So let's talk about the difference that this software really gives us in terms of reporting and finding devices. And feel free to ask questions about this. But I'm going to put up a recording so we can talk about this a little bit better. Now, typically, when you have a free Wi-Fi scanner, you get to see let's say information like this. We get to see SSIDs in an environment. And as we go through the environment, we'll see more and more networks. Okay. Now, the Chanalyzer software does record all of the information, so you can view it later if you need to, and you can also track the signal strengths over time. Okay. We also have the full filters in, so if I know that my my networks are called TWC, like TWC Wi-Fi, I see that they are in channel 1, and I can track their signal strength over time. So you'll notice here, right around, let's say 1047, that the Wi-Fi networks dropped out. Okay? And for those of you who just have Insider, this is what you see. You see the networks drop off. You say, well, the signal strength was good, but I don't see them anymore. What is happening? You need a device that can listen to everything that is going on. Sometimes I use this example to kind of explain what interference is. Let's say you go to China. You hear other people talking, but they're speaking Chinese, okay? And there's buses going by, and there's trains going by, and there's a lot of noise, okay? The only time you know if someone else is talking is if someone is speaking English, and that may not be often enough. You can only hear other people that are speaking English, okay? A spectrum analyzer is going to show you all of the noise from the other speakers. Even if they're speaking Chinese, it's going to show you the noise from the buses going by. It's going to show you the noise from the trains going by, okay? So typically, if you're using Insider, you only get to hear the English speakers, okay? With the spectrum analyzer, we get to hear everything. We get to hear anyone that is speaking. So if we were to look at 1047 in the amplitude history view, look at this. Right around 1047, we see something start. So this is our earthquake. We notice something like an earthquake comes on. Something starts transmitting. And this is immediately a red flag. So let's turn on the color by utilization. And we notice that there's something on channel 1 that is not that curved shape or flat top shape that we talked about earlier. We see something that is creates a shape like this. So this flat top, it's not a flat top shape. We see this kind of like 3 spiked of activity. If you go to the signatures piece in the bottom tabbed section, we can look at all these different patterns of different types of transmitters. Now our software comes with the library. It's already built. You can click on any of these transmitters and attempt to automatically identify the devices or manually identify the devices yourself, okay? Now we do have automatic classification built in here, so we can in some ways attempt to pattern match for you. Now this is not going to be the greatest, and it's just matching patterns. Sometimes it'll give you some false positives, but for the most part it'll come in and it'll say, hey, I think this is a certain type of transmitter, and I'll identify it. So if you notice here, it comes in and it says, I think this was an AV transmitter. Let's see if we can get that to go again. So we'll say, I think this is an AV transmitter, 70% confidence threshold. I think this is an AV transmitter. Okay? So we'll use of what we think it is. Most of you are going to want to use the device finding technique to find out what it is and track it down. So let's talk about how we can build a report that makes sense to people who aren't familiar with spectrum analysis. And this is an example of someone that was trying to provide Wi-Fi for a business, and the business was saying, hey, your equipment doesn't work. And he's like, well, I know the equipment works. I take it outside. I test it before I put it in, and it works. Okay? But whenever I go into environment, it doesn't work. So he builds a report that looks something like this. He says, I know you have TWC Wi-Fi networks, and I'm going to build a report for those particular networks. So we'll start a new report project. You can change the logo. You can add your business logo, give it a title. You can say this is TWC Wi-Fi report. Give it all that kind of stuff. And then you can say, okay, here is your networks table. Here is your networks graph. And in this networks graph, we notice that they drop off right around channel 7. We can edit the block and we can say networks drop off at 1047. Okay, and if you don't like the text, you can change the default text, and then you can also help them visualize it by saying, okay, here is where the networks exist in the Wi-Fi. And then you can create a snapshot of that transmitter, turn on the color by utilization so they can see how prevalent that is. And you can say, okay, there is an AV transmitter in the environment that is causing a lot of activity on those particular channels. So we'll add that as a density view so they can see how much noise. You can say, you know what, this is what it should this is not what it should look like. This is bad. So you can say this is interference. And you can also grab a snapshot of the channels table so they can see how bad it is when that particular transmitter comes on. Now, in this particular example, it was the neighboring company that had wireless surveillance system. So on one side of the building, the Wi-Fi just didn't work, and that was because the neighboring company had a wireless surveillance system that caused interference. The only option that they had, since they couldn't get rid of the neighbor's surveillance system, the only option that he had was for him to to show them what the 5 gigahertz looks like. So we can look at the channels table and we can say, okay, this is what your channels table should look like. You know, grades of 90s and above, so we'll add a channels table, and this is what your channels should look like without security system. Okay, so add that as a block, and then we can also capture what the 5 gigahertz looks like. Now this is where all the new technology is going. This is, you know, the iPhone, the iPad, the tablets. This is what all of them are starting to use, and we can see all 24 channels out here. But look at the channels table. Okay, most of the channels are unused. So you can say, now my equipment works just fine. Okay. You brought something in, your neighbor brought something in that makes it difficult to use. Okay, we can install a 5 gigahertz solution. We can give you all adapters, or we can get you new equipment, and once the new equipment is in, it will use the Wi-Fi just fine. Okay, all of these channels are interference free, so we can create a snapshot of that and add a channels table as well. And here we notice that this is the 5 gigahertz, so we'll change this 5 gigahertz. Oh, 5 gigahertz. Okay. And then we can click the preview to see what the report looks like. So we can see all the tables, the networks dropping off, we can see the density, we can see what's happening on channel 1, and then we can see the channels table that channel 1 was heavily degraded, and we can also go through what it should look like, or what it could look like with the 5 gigahertz. Okay, so that's the basic of software. That's the basics of spectrum analysis. If you have questions about this, feel free to ask them. I'm going to go to other transmitters because we only have a few minutes left. I'd be happy to answer any questions you have, though. Let's talk about different types of patterns that we can see in the spectrum. We can have something like blue teeth. Think of it like blue teeth of a comb, so something that's creating noise across the entire band. We have a baby monitor. Keep in mind, we look at the amplitude history. This device changed channels, so it's one device, and it changes channels. If you look here, we see a curve shape here, and then we see a spike of activity on channel 1. So it looks like the baby monitor jumped channels onto a Wi-Fi network. We also see an analog video transmitter. These can be baby monitors, they can be security cameras, they can be hidden cameras. All of these can create noise on a particular channel. Now someone has asked, what are the strengths and weaknesses of our tools compared to the Fluke tools? I've used the Fluke tools. I'd be happy to talk about that offline. They have better identification. I'll be honest about that. They have better identification. However, I feel like our tools help you find things quicker and better because we have the waterfall navigation. We have a device that helps you find things. Even if we don't identify it, we help you find it. You can only find devices that they identify in their tool. And obviously the price. So we're about half the price with our best tool. Here's what a wideband jammer looks like. This is something that's loud and constant. When I turn this on, it creates noise across the entire band. It takes out keyboards, mice, Wi-Fi, everything. These are used in denial of service attacks. In Europe, you have motion sensors. These are going to be very narrow band, but very loud and constant, as you see here. Xbox 360, so you'll see the wireless controllers, they create a shape similar to Bluetooth, but again, it's blue, so it's not as constant, not as severe. Wireless headsets, these are becoming more and more common in the cubicle environment, so these devices are going to create 2 spikes of activity, and they don't always play nice with Wi-Fi. So sometimes the employees will have wireless headsets when they talk on the phone or listen to music at work, and you can go in there and say, you know what, my equipment works fine, however, your employees have brought all of these in. And with our report builder, you can actually take a picture of what that device is, put it in the report, and the management will say, wow, we have those wireless headsets everywhere. And sometimes that's a good visual representation of, you know, this is how bad the problem is. You have these everywhere. So download a trial of the software. I think everyone should get used to how spectrum analysis works. We have sample files built into the software, so if you don't have the hardware, you can still kind of evaluate what it's like. And also, trial, we'll send you a few emails with sample files and instructions on how everything works and is put together. So if you have questions, Joshua, it looks like you had questions about the Fluke tools. I'd be happy to answer those. I have the Spectrum XT. I think it's a great tool. I'm not here to talk about it, but I can talk about the differences of them. You can follow me on Twitter. You can follow me on YouTube. I have a YouTube channel with a lot of good training videos, and then our website also has some PDFs that you can download and go step by step through all of the products and learn them a little bit better. So I thank you all for attending, and I look forward to working with you in the future, and appreciate your patience with everything.